The largest star ever discovered could swallow 7 quadrillion Earths inside its volume. Stephenson 218 sits 20,000 light-years away in the constellation Scutum. If you placed it at the center of our solar system, its surface would stretch past the orbit of Saturn. The star burns so dim that despite its enormous size, you cannot see it without a telescope. Its radius measures 2,158 times larger than our Sun. For decades, astronomers believed stars had an upper limit. They thought fusion physics prevented anything larger than 1,500 solar radii from forming. Stephenson 218 breaks that assumption. The star exists in a rare phase called a red hypergiant, a category containing fewer than 10 known examples in our entire galaxy. These giants live fast and die young, are burning through their fuel in just a few million years compared to the Sun's 10 billion-year lifespan. The discovery reshapes our understanding of stellar evolution. Stars can grow far more massive than physics seemed to allow. When Stephenson 218 finally explodes, it will detonate as a hypernova, an event so violent it briefly outshines entire galaxies. That explosion is coming soon in cosmic terms. The star has already begun shedding its outer layers, a sign that its core is collapsing. If you find this mind-bending, hit that like button and subscribe. We begin now. There's a star out there, right now, larger than almost anything we've ever found. You cannot see it. Not with your eyes, not with the world's best optical telescope. The light reaching your eye from this star right now, at the photons that would tell you it exists. They left during the last ice age, when mammoths walked the Earth. But you will never see them, not because they're too faint, because they never made it through. They died in the dark, absorbed by dust, 20,000 years into a journey they'll never complete. The star sits in the constellation Scutum, 20,000 light-years away. That distance means light takes 20,000 years to cross the void between this star and Earth. Light moves at 186,000 miles per second. Nothing in the universe travels faster. 20,000 years of that speed, non-stop, and the light still hasn't reached us. Not in any form we could see with our eyes. The problem is dust. Cosmic dust fills the space between stars, especially near the galactic plane, where our galaxy is thickest. This star lives right in that dense band of material. The dust obscures it by 20 magnitudes of visual extinction. That's astronomer speak for a simple fact. The star appears 100 million times fainter than it actually is. 100 million. If you could somehow remove all that dust, the star would blaze in our sky. Instead, it's invisible. Picture trying to see a candle through a wall of fog 100 million times thicker than Earth fog. The candle is there. It's burning. The light exists, but the fog absorbs every photon before it reaches you. That's what's happening here. 20,000 light-years of dust, tiny grains of material, each about a micrometer across, blocking everything. A micrometer is 1/1,000,000th of a meter, smaller than a human cell. Yet you'd need about 25,000 of these grains lined up to span an inch. These tiny particles stop visible light completely. Light hits a dust grain like a boulder blocking a hallway. There's no path forward. The photon gets absorbed. Its energy converts to heat. The journey ends. Wavelengths in the visible spectrum, the light your eyes detect, they simply cannot penetrate. Every single photon dies in the dark. For decades, astronomers searched the sky with optical telescopes. They mapped millions of stars. They catalogued everything they could see. This star never appeared in their surveys. It wasn't there, not because it didn't exist, but because they were looking with the wrong tools. The star was always screaming. They were deaf to it. Actually, that's not quite right. Let me try again. And it's not that the star is invisible. It's that we were looking with the wrong eyes. The star was always there, shouting. We were just deaf to it. Infrared light changes everything. Infrared wavelengths are longer than visible light. They slip through dust like a whisper slipping through a crack. The dust grains that block visible light let infrared pass almost untouched. Turn an infrared telescope toward Scutum, toward the same patch of sky that looks empty in visible light, and suddenly the star appears. Not dim, not faint, blazing. The star, is one of the brightest infrared sources in the entire sky. Think about that. Completely invisible in one wavelength, one of the brightest objects in another. It's not far away or intrinsically dim. It's right there, pouring energy into space at a staggering rate. Yet hidden behind a curtain we couldn't see through until we learned to look in infrared. This happens more than you'd think. The galactic plane is full of massive stars we've never seen with our eyes. They live behind veils of dust so thick that visible light has no chance. Infrared astronomy, which only became practical in the last few decades, reveals an entirely different universe, a universe of giants hiding in plain sight. The dust itself comes from dead stars. When stars explode or shed their outer layers, they spray elements into space: carbon, silicon, oxygen. These elements condense into tiny solid particles. The particles drift through the galaxy, clustering in dense clouds. New stars form from these clouds. The cycle continues. The dust that hides this star came from stars that died before it was born. We found this particular star by scanning the infrared sky systematically. Astronomers pointed telescopes toward the galactic plane and recorded everything they saw. The star appeared as a bright infrared source in a region rich with other massive stars. It didn't look special at first, just another red dot in a crowded field. The real work came later, measuring its properties, figuring out what it actually was. That process took years. The measurements revealed something unexpected. This wasn't just a massive star hiding behind dust. It was one of the largest stars ever found. Its true brightness, once corrected for all that dust absorption, placed it among the most luminous objects in the galaxy. The size calculations came next. They showed a radius stretching past the orbit of Saturn. As a star so enormous, it breaks our models of how large stars can grow. But we're getting ahead of ourselves. The point is this: the universe contains wonders we cannot see directly, objects so obscured by dust and distance that visible light, the light we evolved to detect, never reaches us. For most of human history, we had no idea these objects existed. We looked up and saw a fraction of what was really there. The rest waited in silence, invisible, until we built new eyes. So we have this star, this infrared source in the Scutum constellation. The measurements come in, the calculations finish, and the numbers don't make sense at first. They're too large. You check them again. They hold. Let's establish a unit of measurement. Astronomers measure stars in solar radii. One solar radius is the distance from the center of our sun to its surface, about 432,000 miles. The sun, by definition, is one solar radius, a familiar star, a normal star, the star that makes life possible. Stephenson, 218 measures approximately 2,150 solar radii. That number needs context. If you placed this star at the center of our solar system, where the sun sits now, its surface would extend past Saturn's orbit. Mercury would be inside the star. Venus would be inside the star. Earth, our home, would be inside the star. Mars would be inside the star. Jupiter, the giant of our solar system, would be inside the star. Saturn, with its rings, would be inside the star. All of them, gone. Not destroyed, just incorporated into the outer atmosphere of a single object. Yet the inner solar system as we know it wouldn't exist. The space where we live, where all human history happened, would be interior to a star. Picture this. If the sun were a basketball, about 9.5 inches across, Stephenson 218 would be a sphere taller than the Empire State Building. You'd stand at the base, look up past 102 floors, past the antenna, into the sky beyond, and you still wouldn't see the top. That's the scale difference. From something you can hold to something that defines a skyline. Light moves at 671 million miles per hour. Nothing in the universe travels faster. Light crosses the distance from the sun to Earth in 8 minutes. It circles the Earth nearly 7.5 times in 1 second. Light doesn't wait. Light doesn't slow down. It takes light 8 hours to travel around Stephenson 218 once. 8 hours for the fastest thing in existence to complete a single lap around the star's equator. You could eat breakfast, go to work, put in a full shift, drive home, and sit down to dinner. And light, which circled Earth 7.5 times while you read that sentence, would just be finishing its journey around this star. The uncertainty in the measurement is worth mentioning. Some estimates put the radius at 1,800 solar radii. Others go as high as 2,400. That's a range of 600 solar radii, the distance from the Sun to beyond Mars, just as measurement uncertainty. But here's the thing. The uncertainty isn't because we made bad measurements. It's not because our instruments lack precision. The star doesn't have a defined edge. There's no surface. No place where the star stops and space begins. The outer layers of Stephenson, 218, are so diffuse, so thin, that they fade gradually from sort of there to not really there. The density drops off slowly. At what point do you call it the edge? When the gas reaches a certain thickness, a certain temperature, a certain number of atoms per cubic meter. We're measuring something that has no boundary. The number itself becomes almost philosophical. Where does a star end when it never actually ends? When it just fades away into nothing? The volume calculation defies intuition even more. Volume scales with the cube of the radius. Make something twice as wide, it becomes 8 times the volume. Make it 10 times as wide, it becomes 1,000 times the volume. Stephenson 218 is roughly 2,000 times wider than the Sun. The volume works out to about 10 billion times the Sun's volume. 10 billion. You could fit 10 billion suns inside this star if you could pack them together. That comparison falls apart under examination. You can't pack stars together. They're not solid objects. But the number stands. 10 billion times the volume. Consider travel time. A commercial airplane flies at about 500 miles per hour. If you could somehow fly an airplane across the diameter of Stephenson 218, the trip would take about 400,000 years. Modern humans, Homo sapiens, have existed for roughly 300,000 years. You'd need more time than humans have been humans. You'd start the flight before our species existed and land sometime in the future. The galaxy would rotate. Stars would be born and die. Civilizations could rise and fall, and you'd still be crossing this single object. These numbers violate something fundamental in how we think about stars. The Sun is a star. We can conceptualize the Sun. We can imagine it, even if we can't truly grasp its scale. But 2,000 times wider, 10 billion times the volume, light taking 8 hours to circle once, the framework breaks. The intuition fails. We use the solar system as a measuring stick because it's the only reference we have. Saturn's orbit means something to us. We've sent probes there. We have pictures. But even that comparison doesn't quite land. The part of our brain that understands size stops working at this scale. The star sits out there, 50,000 light years away, hidden behind dust, is slowly pulsing in the infrared. It doesn't care that we found it. It doesn't care that the numbers seem impossible. It simply exists, larger than our models predicted, larger than seems reasonable, larger than we can properly imagine. The measurements are what they are. The star is what it is. And we're left trying to explain it. We need to name it. The measurements are done. The comparisons are made. The numbers sit there, larger than comprehension. But now we have to call it something. We have to give this thing a designation. The largest known star in the universe. Stephenson 2-18. That's the name. It sits in the Stephenson 2 cluster, about 50,000 light years away, and it wears the crown. The biggest, the most enormous physical object we've ever found that can still be called a single star. But let that sink in for a second. When you hear largest star, your brain probably goes to heaviest, most massive, the most stuff packed into one place. That's what largest means, right? The thing with the most material, the most gravity, the most power, the heavyweight champion. But that's not what largest means, not with stars, not with Stephenson 218, because the largest star isn't the heaviest star. It's not even close. This is where intuition breaks, where the word largest stops meaning what you think it means. Largest means radius, size, physical extent through space, how much room the thing takes up. Stephenson 218 has a radius roughly 2,000 times larger than our Sun. We covered that, but the surface area scales with the square of the radius. At 2,000 times the radius means 4 million times the surface area. 4 million. The Sun's surface could be painted onto Stephenson 218 4 million times and still not cover it. If your skin suddenly had 4 million times more area, you'd cover the entire state of Rhode Island. Every street, every building, every square inch of ground. That's how much more surface this star has than our Sun. The volume is worse. Volume scales with the cube of the radius. 10 billion times the volume of the Sun. 10 billion suns could fit inside Stephenson 218 with room to spare. It's not a star at this point. It's a star-shaped region of space that happens to glow. But here's the thing. Here's the violation. Stephenson 218 isn't the most massive star, not even in the top 10. The most massive star we know is called R136A1. It weighs about 300 times what the Sun weighs, maybe more. Stephenson 218, maybe 25 solar masses, maybe less. It probably started with 25 to 40 solar masses when it was born, but it's been losing mass for its entire adult life, blowing material into space, shedding its outer layers. By now, it might weigh 15 times what the Sun weighs, maybe 20. We don't know exactly, but definitely not 300. So how is the largest star also one of the lighter ones? How does something enormous weigh less than something smaller? It's like comparing a balloon to a cannonball. The balloon is bigger. The cannonball weighs more. You can hold the cannonball in your hand. The balloon might be 3 feet across. But the cannonball has more mass, more density, more stuff per unit of volume. Stephenson 218 is the balloon. R136A1 is the cannonball. One is larger. The other is heavier. They're not the same thing. This breaks the model most people have in their heads. We think of extreme as meaning dense, concentrated, powerful. The biggest things should be the heaviest things, the most massive. But Stephenson 218 is extreme precisely because it's not dense. It's extreme because it's dying, because it has puffed up to an absurd size while losing mass. The density is lower than the air you're breathing right now, lower than any vacuum we can create on Earth. If you could scoop out a cubic meter of material from deep inside Stephenson 218, it would weigh less than a breath. The star is dying, and that's why it's so large. It ran out of hydrogen in its core millions of years ago. Now it's burning heavier elements in shells around a dead center. The radiation pressure from those shells pushes the outer layers outward. The star expands and expands and keeps expanding until the outer layers are so far from the core that gravity barely holds them. The star becomes a vast cloud of glowing gas, held together by the faintest gravitational thread. It's not a young star. It's not a vigorous star. It's an old star on its deathbed, swollen and fading. If stars were people, Stephenson 218 wouldn't be the muscular athlete. It wouldn't be the strong man. It would be the 80-year-old in hospice, bloated and frail, barely holding on. The most extreme star we've ever found is also the most exhausted. The largest is the least dense. At the biggest is the dying. That's the surprise. That's the thing nobody expects. When you search for the largest star in the universe, you're not looking for power. You're looking for exhaustion, for a star that has burned through so much of its life that it can barely hold itself together anymore. Think about that. The record holder isn't the champion. It's the retiree, the thing that used to be powerful and now can barely function. Stephenson 218 probably started as a massive star by human standards, 25 to 40 times the mass of the Sun. That's huge. That puts it in the top fraction of a percent of all stars. But it's been losing mass for tens of millions of years. Stellar winds, ejections, mass loss. The outer layers blow away into space. The star gets lighter. And paradoxically, it gets bigger. Less mass. More size. The opposite of what you'd expect. R136A1, the most massive star, is nowhere near as large. It weighs maybe 15 times what Stephenson 218 weighs. But it's smaller. Much smaller. Still enormous by any reasonable standard, maybe 30 or 40 times the radius of the Sun, but not 2,000 times, not even close. It's young, it's hot, it's dense, it's crushing itself under its own gravity, burning fuel so fast it'll be dead in a few million years. But right now, it's compact, powerful, All that mass squeezed into a relatively small space. Stephenson 218 is the opposite. It's loose, diffuse, spread out across a volume that defies comprehension. If the Sun were a grain of sand, Stephenson 218 would be a beach ball sitting across a football field. Same object, conceptually. Both are stars. Both are spheres of glowing plasma held together by gravity. But the scale difference is so extreme that the comparison stops meaning anything. You can hold a grain of sand, you can hold a beach ball, but you can't hold both and feel the difference. The football field of distance between them becomes part of the analogy, part of what you're trying to understand. We use the word largest because we need a superlative. We need a record holder. But the word doesn't capture the reality. Stephenson 218 isn't just large. It's distended, inflated, stretched to the breaking point. The outer layers are barely bound to the core. In a few 100,000 years, maybe sooner, those layers will drift away entirely. The star will shed its envelope and leave behind a core, probably a neutron star, maybe a black hole. Yeah, the largest star in the universe will collapse into something the size of a city. All that size, all that volume, all that surface area, gone, blown into space, recycled into the next generation of stars. But for now, it's still there, still the largest, still glowing in the infrared, hidden behind dust, pulsing slowly as its outer layers expand and contract. It doesn't know it holds a record. It doesn't know we found it. It's just doing what dying stars do, swelling up, losing mass, fading. The most extreme things in the universe are often the most fragile. The biggest are the weakest. The records are held by the things barely holding on. That's what largest means. Not strongest, not heaviest, not most powerful, just biggest. The thing that takes up the most space. The thing that has stretched itself so thin that it's more absence than presence. Stephenson 218 is a star-shaped void, a region of almost nothing that still manages to shine. And we call it the largest because we don't have a better word. Because largest is what we say when something breaks the scale, and we still need to file it somewhere in our understanding. The measurements are what they are. The star is what it is. And now we know what the word largest actually means when we're talking about something this far outside normal experience. So, what exactly is Stephenson 218 made of? What would you find if you could travel there and look around? And the answer breaks most of what you think you know about stars. Let's start with temperature. The surface of Stephenson 218 sits at about 3,200 Kelvin. That's hot. Hot enough to vaporize any spacecraft we could build. Hot enough to melt titanium in seconds. But for a star, it's cold. The sun's surface is almost twice that temperature. Stephenson 218 is so cool that molecules can form in its atmosphere. Water vapor, titanium oxide, complex chemistry happening in the outer layers of a star. That's not supposed to be possible. Stars are supposed to be too hot for molecules. But when you're this big and this diffuse, the rules change. The temperature is strange, but the density is stranger. The average density of Stephenson 218 is roughly 1/10 billionth of a gram per cubic centimeter. Now write that number out and it's a 1 with 10 zeros after the decimal point before you hit anything that isn't zero. That's not just light. That's almost nothing. A cubic meter of this star contains less mass than a breath of air, less than a whisper. You could wave your hand through it and barely notice the resistance. The photosphere, the visible glowing layer we call the surface, is even thinner. Its density is about 1 billionth of Earth's atmosphere at sea level. 1 billionth. If you took a cubic meter of air from where you're sitting right now and removed 99.9999999% of it, you'd be getting close to what the star's photosphere feels like. It's not air. It's not even close to air. It's barely anything at all. Here's where it gets truly strange. And the outer layers of Stephenson 218 are less dense than the best laboratory vacuums on Earth. Scientists can build chambers that suck out almost all the air, creating near-perfect emptiness for experiments. The outer parts of this star are emptier than that. This star, this massive glowing object, is made of better vacuum than we can create in our most advanced facilities. The thing we call the largest star in the universe is mostly just emptied space that happens to be hot enough to glow. There's no surface. That's the part that's hard to accept. You look at images of stars and you see a sphere, a ball, something with an edge, something you could theoretically touch or land on. None of that is real. Stephenson, 218 doesn't have a surface any more than fog has a surface. It's just gas. Dense gas in the middle, getting thinner as you move outward, fading gradually into the nothing of interstellar space. There's no boundary, no line where the star stops and space begins. If you flew a spacecraft towards Stephenson 218, you'd never encounter a moment where you arrived. You'd just notice the space around you getting thicker, getting redder. The glow would intensify. The hydrogen and helium would grow denser, but so gradually you couldn't pinpoint when you crossed over. You'd look out your window and it would be darker red than before, then darker still. Then you'd be surrounded by glowing gas on all sides. Then the radiation would kill you and the heat would vaporize your ship, but you'd never hit anything. You'd never crash. There's nothing to crash into. You'd just gradually realize you were inside the star, and then you'd be gone. But think of it like walking through fog, thick fog on a morning when you can barely see. You walk forward and it's foggy. You keep walking and it's still foggy. Eventually, you're in clear air, but there was no moment when you stepped out of the fog. It just gradually stopped being fog. There was no door, no threshold, just a gradual transition from thick to thin to nothing. That's what a star is. A region where space happens to be glowing. A place where the gas is dense enough and hot enough to emit light. Not a thing, a condition. The surface we talk about, the photosphere, is just the layer where the gas becomes opaque, where it gets thick enough that light can't pass through anymore. That's all. It's not a physical boundary. It's an optical illusion. We call it a surface because we need to call it something, and because we need to measure from somewhere. But it's arbitrary. The star doesn't know where its surface is. The gas doesn't care about our definitions. A cubic meter of the star's atmosphere contains less matter than a cubic meter of the space between Earth and Mars. Let that sink in. The space between planets, the vast emptiness we call the solar system, is more crowded than the inside of this star. Stephenson, 218 has taken the concept of star and stretched it so thin that it barely qualifies as matter anymore. It's a ghost, a memory of density, a region of almost nothing that still manages to shine. This is what largest actually means when we're talking about stars. Not the most massive, not the densest, not the most powerful, just the most spread out, the most diffuse. It's the one that's managed to puff itself up so far that it's more absence than presence. Stephenson 218 is barely holding itself together. The outer layers are so loosely bound that they're practically already gone, drifting away into space. The star is less a solid object and more a suggestion of where an object used to be. You can't land on it. You can't touch it. You can't even say for certain where it ends. The star fades from dense fog to thin fog to interstellar medium without ever crossing a line. It's there and not there, present and absent, the largest thing we've ever found, and it's made almost entirely of nothing. So where does the star end and space begin? That's not a question with an answer. It's a question that reveals the question is wrong. There is no end. There is no beginning. There's just a gradient, at a slow fade, a place where space gets a little warmer, a little thicker, and starts to glow. We draw a line and call it a surface because we're humans and we need boundaries. We need edges. We need to know where things are. The universe doesn't care what we need. Stephenson, 218 is what it is. A star-shaped cloud, a region of glowing near vacuum, the largest star we've ever found, and it barely exists at all. But that's not the star's final form. That's barely the beginning of the story. To understand how Stephenson 218 became what it is, you have to rewind, way back, to a time when this monster didn't exist at all. The Stephenson 2 cluster formed roughly 20 million years ago. That sounds ancient. It's not. 20 million years ago, the Earth already had grass, had whales, had recognizable continents, and the ancestors of modern elephants were walking around. The star that would become Stephenson 218 was born into a universe that already contained everything we'd recognize as familiar. It started as a cloud, just gas and dust collapsing under its own gravity. Nothing special about that. Happens all the time. But this particular cloud had mass, somewhere between 25 and 40 times what the Sun has. That's the key number. That's what determines everything that follows. When you pack that much mass into a collapsing ball of gas, the core gets hot, really hot, 20,000 Kelvin or more. At those temperatures, something happens that doesn't happen in smaller stars like the Sun. The CNO cycle kicks in. The CNO cycle is a fusion pathway that uses carbon, nitrogen, and oxygen as catalysts to fuse hydrogen into helium. It's more efficient than the proton-proton chain that powers the Sun. A lot more efficient. Here's the part that matters. The CNO cycle scales with temperature to the 16th power. Let me say that again because it's exponential violence. Double the core temperature, and you don't get double the power output. You get 65,000 times the power output. 65,000. The star becomes a fusion reactor running at full throttle with no off switch. Stephenson, 218, spent 10 to 15 million years as a hot blue supergiant, compact by supergiant standards, maybe 10 to 20 times the Sun's radius. Not small, but nothing like what it is now. Surface temperature over 20,000 Kelvin, blazing blue-white, are pouring out more energy in a second than the Sun produces in a year. This is the main sequence phase. The star is burning hydrogen in its core, converting it to helium. The fusion generates outward pressure that balances gravity's inward crush. The star sits in equilibrium, stable. For millions of years, nothing changes. The star just burns. But here's the thing about burning hydrogen. You make helium, and helium doesn't burn at these temperatures. It just sits there, like ash building up in a fireplace. Helium accumulates in the core as hydrogen burns, until eventually you're left with nothing but ash and the fire goes out. Except the fire doesn't go out. It moves. When the core hydrogen runs out, fusion stops. The core contracts. As it contracts, it heats up. The temperature in the shell just outside the core rises until it's hot enough to ignite. Hydrogen starts fusing in a shell around the inert helium core. Shell burning begins. Shell burning is more intense than core burning. The energy output goes up, way up. All that extra heat has to go somewhere. It can't push inward. The core is in the way, so it pushes outward. The outer layers of the star start to expand. It's like turning up the heat under a pot of water until the lid starts to rattle and lift off. The envelope expands, and expands, and expands. As it expands, it cools. The surface temperature drops from 20,000 Kelvin to 3,500. The star changes color from blue to red. The radius balloons from tens of solar radii to over 2,000. The transformation doesn't take long. Maybe a few thousand years, maybe less. The star spent 15 million years as a blue supergiant. Then, in a cosmic eye blink, it became something else entirely. The core keeps contracting and heating. Eventually, it gets hot enough to fuse helium into carbon, then carbon into heavier elements. The core becomes a furnace burning multiple fuels simultaneously. Each stage produces more heat, drives more expansion, cools the surface further. The star grows and grows and grows. Right now, Stephenson 218 is burning helium, carbon, and heavier elements in its core. The exact details depend on models and assumptions. We can't see inside the star. We can only measure what's happening at the surface and work backward. But the physics is clear. The star is deep into its post-main sequence evolution, and it's processing its fuel faster than it ever did as a blue supergiant. The red supergiant phase lasts about 100,000 years. Maybe a little more, maybe a little less. That's it. 100,000 years out of a total lifespan of roughly 20 million. Less than half of 1% of the star's life. Think about that. The star spends 10 to 15 million years being relatively normal. Just a very large, very hot star doing what large hot stars do. Then suddenly, in the last 100,000 years, it inflates into this absurd, impossible thing. It's like a human spending 80 years as a normal adult, then suddenly inflating to the size of a building in the last month of life. The most dramatic phase is the shortest. This is the part that gets me. The star spends millions of years being relatively normal, and then suddenly, in a cosmic eye blink, it becomes this absurd, impossible thing, and we happen to be watching during that eye blink. If we'd been here a million years ago, we'd see nothing special. A blue dot in a cluster of blue dots. A million years from now, it'll be gone. Completely gone. We're watching the star's last breath. The timing is almost suspicious. Red supergiants make up a tiny fraction of all massive stars because the phase is so brief. Most massive stars are still on the main sequence, burning hydrogen, looking normal. Only a few are caught mid-transformation. Only a few are enormous. We found one. We found the biggest one, and we found it now, while it's at its maximum size, in the last flicker before it collapses. That's either extraordinary luck, or there are more of these things out there than we think. Either way, we're looking at something that shouldn't be common, something fleeting, something that exists in the gap between stable and gone. Stephenson. 218 didn't grow gradually over time. It exploded outward in a geological instant, and it's still expanding, still cooling, still processing through the last reserves of fuel in its core. Every day it gets a little bigger, a little cooler, a little closer to the moment when the fusion stops for good. The path to enormity isn't slow. It's sudden, violent, brief. The star rushes through its final phase like it's running out of time, which it is. The clock is ticking. The fuel is almost gone. What happens next has been inevitable since the moment the star formed. But it wasn't alone. Stephenson 218 sits inside a cluster, a collection of stars all born from the same cloud of gas, all roughly the same age, all bound together by gravity. The cluster is called Stephenson 2, and it's not just home to one monster star. It contains at least 26 red supergiants, 26 of the rarest, most extreme stars in the galaxy, all in one place. Finding 26 red supergiants in one cluster is like finding 26 lottery winners living in the same neighborhood, individually rare, collectively astonishing. The cluster was catalogued in 1990 by an astronomer named Charles Bruce Stephenson. He wasn't looking for giant stars. He was mapping infrared sources near the galactic plane, working through the haze of dust that blocks visible light. Stephenson was making a map of the infrared sky and stumbled onto a collection of the most extreme objects in the galaxy, hiding in plain sight. He documented the sources, numbered them, added them to a catalogue. He didn't know what he'd found. Not yet. Infrared astronomy reveals what visible light can't. The dust that blocks optical telescopes glows in infrared, and massive stars, especially cool red supergiants, shine brightest in that wavelength. Stephenson's catalogue identified dozens of infrared sources clustered together, but at the time, the technology couldn't tell him how far away they were or how big they were, just that they were there, bright in infrared, grouped together, unusual. The Spitzer Space Telescope changed that. Launched in 2003, Spitzer mapped the cluster in mid-infrared wavelengths, at revealing details Stephenson couldn't have seen from the ground. The telescope picked out individual stars, measured their temperatures, started to build a picture of what the cluster actually contained. It wasn't just a collection of infrared sources. It was a graveyard of giants, stars in their final phase, stars dying young. Astronomers realized the true scale of Stephenson 218 in 2012. They combined data from multiple telescopes, refined their distance measurements, ran the numbers. The star wasn't just big, it was one of the biggest ever observed, and it wasn't the only one in the cluster pushing the limits. Multiple stars in Stephenson 2 were larger than anything found anywhere else. The cluster became famous overnight, not because of one star, because of what the whole collection represented. Her distance measurements got better. The Gaia mission, launched in 2013, revolutionized how we measure the positions of stars. Gaia measures parallax, the apparent shift in a star's position as Earth orbits the Sun. It's like closing one eye, then the other, to judge how far away something is. But Gaia's eyes are 6 months apart, on opposite sides of Earth's orbit. The shift is tiny, a fraction of an arc second. But Gaia measures it precisely, and from that shift, Astronomers can calculate distance. Better distance means better size estimates, better certainty. The cluster is young, only 20 million years old. That's a blink in cosmic terms. Our Sun is 4.5 billion years old. Stephenson 2 has existed for less than 0.5% of that time, 20 million years. And already, 26 of its stars are in their death throes. That tells us something critical. All 26 were born massive enough to evolve rapidly. Stars like the Sun take billions of years to exhaust their fuel. These stars burned through theirs in 20 million. They lived fast. They're dying young. Most star clusters contain 0 red supergiants. The phase is too brief, the star's too rare. You might find one if you're lucky, maybe 2. Stephenson 2 has 26. It's a cosmic anomaly, a supergiant factory. Something about the conditions in this cluster allowed it to form dozens of stars massive enough to become these extreme objects. The gas cloud must have been dense, massive, collapsing in just the right way to fragment into multiple high-mass stars instead of scattering into thousands of smaller ones. Think about that. In a galaxy with hundreds of billions of stars, we found a cluster where the conditions aligned perfectly to create 24 monsters. The universe doesn't care what we find convenient. It doesn't spread rare objects evenly across space. Sometimes it clusters them. Sometimes it makes exceptions. Stephenson 2 is one of those exceptions, a place where the rules bent just enough to let something extraordinary happen. The technology to study the cluster keeps improving. Ground-based telescopes with adaptive optics can now peer through the dust with better resolution than Stephenson had in 1990. Space telescopes operating in infrared and other wavelengths map the cluster in multiple dimensions. Gaia continues refining distances, narrowing the margins of error. Every new measurement brings us closer to understanding what we're looking at, and every measurement confirms the same thing. This cluster is special. Stephenson didn't live to see what his catalogue became. He died in 2001, before Spitzer revealed the cluster's details, before astronomers realized the scale of Stephenson 218. He documented infrared sources. He did his job. He moved on to the next survey. The significance came later, built on his foundation. That's how discovery works sometimes. You map the sky, you catalogue what you find, and years later, someone else realizes what you were looking at. The cluster sits about 19,000 light-years away. That's more than halfway across the galaxy from us. 19,000 years. The light we see now left the cluster before the last ice age ended, yet before humans built cities, before we invented writing. The photons traveled through space for 19,000 years, and they're just reaching our telescopes now. We're not looking at the cluster as it is. We're looking at it as it was when our ancestors were still learning to farm. And in that frozen moment, captured in light from the deep past, we see 26 stars all approaching the end, all cooling, all expanding, all running out of time. The cluster won't last. Some of those stars have already exploded. We just don't know it yet. The light from their deaths is still in transit, still crossing the gap. In a few 100,000 years, maybe less, all 26 will be gone. Supernovae, neutron stars, black holes. The cluster will be dimmer, quieter, ordinary. But right now, in the light reaching us tonight, Stephenson 2 is still a giant nursery turned into a supergiant graveyard. Still the most extreme collection of dying stars we've ever found. Still hiding in the dust, glowing in infrared, waiting for the next generation of telescopes to reveal even more. That's what infrared astronomy gives us. Not just brighter pictures, not just clearer images. It gives us the ability to see through the veil, to map what was always hidden, to find entire populations of stars that optical telescopes miss completely. Here's why it works. Dust grains in space are tiny. They're about the same size as the wavelength of visible light. When optical light hits them, it scatters everywhere. Blue light bounces off, red light deflects. The photons never make it through. But infrared light has a longer wavelength, much longer. The dust grains are too small to scatter it efficiently. The infrared just slides past. It's like trying to see through a sandstorm with your eyes versus using sonar. The sand blocks your vision completely, but the sound waves don't care. They ignore the particles and pass right through. Infrared does the same thing with cosmic dust. Before infrared astronomy became standard, we were working blind. Mapping the Milky Way from Earth was like trying to map the ocean floor from a boat. You could see the surface, the waves, the occasional floating debris, but all the important stuff, the deep structure, the trenches, the underwater mountains, all of it was hidden below. We knew it was there, we just couldn't see it. Optical telescopes showed us a galaxy, sure. Yeah, but they showed us the easy parts. The stars above the dust, the clear lines of sight. Everything else was just darkness. The surprise is this: the galactic core, the actual center of the Milky Way, is completely invisible in optical light. Point a visible light telescope toward the heart of our galaxy and you see almost nothing. A dark smudge, maybe a few dim stars in the foreground. That's it. The center of our home galaxy, where millions of stars orbit a supermassive black hole, where the density of matter is unlike anywhere else in the Milky Way, is just gone in visible wavelengths. The dust between us and the core is too thick, too complete. We were blind to the heart of our own galaxy for centuries. We knew something was there. The math told us. The orbital dynamics of nearby stars hinted at a massive concentration of matter, yet but we couldn't see it. Then, infrared astronomy arrived. The galactic center exploded into view. Dense swarms of stars, glowing dust clouds lit by radiation, arcs of gas spiraling toward the black hole. The most active, most violent, most densely packed region of the galaxy suddenly became visible. We'd been living in a galaxy our entire history as a species, and we'd never seen its heart until we learned to look in infrared. That changes everything. Suddenly, star formation regions became mappable. These are the nurseries where new stars are born, always hidden behind thick clouds of gas and dust. Optical light can't penetrate them, but infrared can. We started finding protostars, baby stars still wrapped in their birth cocoons. We started counting the stellar populations near the galactic plane where dust is thickest. We realized we'd been missing most of the universe's massive stars. They were always there. We just couldn't see them. The Spitzer Space Telescope spent 16 years mapping the galaxy in infrared. It found star clusters we didn't know existed. It traced spiral arms through regions that looked empty in optical surveys. It revealed the true structure of the Milky Way, the layout we'd been guessing at for decades. Spitzer wasn't looking for supergiant stars specifically. It was building a map, but in that map, hidden behind veils of dust, were stars like the ones in Stephenson 2. Stars too faint in visible light, too obscured, too far. Infrared made them findable. James Webb took it further. Its infrared vision is sharper, more sensitive, and it's like putting on heat vision goggles in a dark room and suddenly seeing everything that's warm. Webb doesn't care if there's dust in the way. It looks right through. It sees the heat signature, the infrared glow, the radiation that longer wavelengths can capture. That's how we study the earliest galaxies, the ones formed when the universe was young and full of dust. That's how we peer into star-forming regions and watch planets coalesce from disks of debris. That's how we find things optical telescopes would never reveal. There's a progression here. Galileo pointed his first telescope at the sky in 1609. He saw moons around Jupiter, craters on our moon, phases of Venus. It was revolutionary, but he was limited to visible light. That's all anyone had for centuries. Photography expanded what we could capture. Our bigger mirrors gathered more photons. We built observatories on mountaintops to escape atmospheric distortion. Each step revealed more, but we were always looking through the same window, the narrow slice of the electromagnetic spectrum our eyes evolved to see. Infrared opened a new window, a completely different view. It's not just a better version of optical astronomy, it's a different science. The universe looks different in infrared. Cooler objects become visible. Dust becomes transparent. Entire regions of space that seemed empty suddenly fill with structure. We went from seeing a fraction of the galaxy to seeing most of it, from guessing at the distribution of stellar populations to actually counting them. The Roman Space Telescope is launching soon. another infrared observatory, even wider field of view than Webb, and it'll survey huge portions of the sky, finding objects Webb would take years to locate individually. Then there's ground-based infrared interferometry, combining light from multiple telescopes to achieve resolutions that single mirrors can't match. The technology keeps improving, the windows keep opening wider, which brings us back to the question that matters. Are there larger stars than Stephenson 2-18 hiding behind even thicker dust, waiting for better telescopes? We don't really know. That's the honest answer. Every time we build a better telescope, we find things we didn't expect. Pulsars, quasars, exoplanets, dark energy. Gravitational waves weren't even predicted when we built the first radio telescopes, but we found them anyway. The universe is full of surprises. Maybe Stephenson 2-18 is the limit, and maybe red supergiants can't get any bigger without tearing themselves apart or collapsing. Maybe we've found the extreme edge of what's physically possible. Or maybe it's just the largest we can see so far. Maybe there's a star twice as big sitting behind a dust cloud so thick even infrared struggles to penetrate it. Maybe it's in a region we haven't surveyed yet. Maybe it's in another galaxy, too faint and too far for current instruments to resolve. We won't know until we look. That's always been the pattern. We build the telescope, we point it somewhere, we find something we weren't expecting. Then we build a better telescope and do it again. Infrared didn't just help us find Stephenson 2-18, it revealed the possibility that stars like it could exist in the first place. It showed us the hidden populations and the obscured clusters, the regions of the galaxy we'd been missing. Before infrared, we were astronomers with a blindfold on, trying to describe the universe by touch. We did pretty well, considering, but we were always missing pieces. Infrared took the blindfold off, and now we're still adjusting to what we can see. We've been looking at Stephenson 2-18 from the outside. The size, the scale, the sheer impossibility of something that large existing at all. But there's something happening at the surface of this star that matters just as much as its diameter. Something that changes everything we thought about how these giants die. Stephenson 2-18 is evaporating. Not slowly, not gradually over billions of years. Fast. And the star sheds mass at a rate that would empty our sun completely in just a few thousand years. Some estimates put it at 5,000 years. Some say 10,000. Either way, that's a blink. That's nothing on cosmic timescales. Imagine shedding your entire body weight every single heartbeat, continuously, forever. That's what's happening here. The star isn't stable. It's not sitting there burning fuel and maintaining its structure. It's actively disintegrating while it burns. The mechanism is both simple and strange. Start with the surface temperature, around 1500 degrees Kelvin in the outermost layers. That's cool enough for dust grains to form, tiny particles, silicates, carbon compounds. They condense out of the stellar atmosphere the way water droplets form in a cloud. These dust grains absorb starlight. As photons hit them, push them. Radiation pressure is weak on individual atoms, but dust grains have more surface area, more cross-section. The light from the core pushes them outward. Here's where it gets interesting. The dust grains don't leave alone. They drag gas with them. Collisions, friction. The whole outer layer starts moving. Material that would otherwise fall back to the star gets pulled along for the ride. The dust acts like a net, catching atoms and molecules and hauling them into space. This is the stellar wind, not a metaphor, an actual wind. Gas streaming away from the star at dozens of kilometers per second, driven by nothing but light pressure on dust. You might wonder why the star's gravity doesn't stop this. Why doesn't all that mass just fall back? The answer is the escape velocity, and the speed you'd need to leave the star's surface and never come back. For our sun, that's over 600 kilometers per second. You'd need to be moving at a significant fraction of light speed to escape. The sun's gravity holds on tight. Stephenson 2-18, 20 to 30 kilometers per second. That's it. A good Major League Baseball pitcher throws around 45 meters per second. Call it 0.045 kilometers per second. You'd need to throw about 600 times faster to escape the star's surface. That sounds like a lot until you compare it to the sun. There, you'd need a throw over 13,000 times faster than a fastball. The gravity at Stephenson 2-18's surface is pathetic, weak, almost negligible. This creates a feedback loop. The low gravity means convection cells in the outer layers can lift material to enormous heights. Picture thermal updrafts in Earth's atmosphere. Hot air rises, cool air sinks. The same thing happens in a star's outer envelope, but on a vastly larger scale. In a normal star, gravity pulls everything back down. The convection cells churn and mix, but they don't launch material into space. In Stephenson 2-18, the updrafts lift gas and dust high enough that they're already moving near escape velocity. The radiation pressure takes over from there. It's like thermal updrafts launching hang gliders straight up until they reach escape velocity and fly away. The star isn't just losing material from its surface, it's actively throwing it off. The mass loss rate varies, sometimes more, sometimes less. The outer layers pulsate, expand and contract. When the star swells, the surface gravity drops even further. Escape becomes easier. The wind picks up. When it contracts slightly, gravity reasserts itself. The wind slows, but it never stops. The star is always evaporating, always shedding mass. The space around it fills with gas and dust. The stellar wind doesn't disappear. It flows outward into the interstellar medium, eventually cooling and dispersing. Some of it will form new dust clouds. Some of it will be incorporated into future stars. Some of it will drift for millions of years before interacting with anything. Here's the part that matters. The star is not dying because it runs out of fuel and then explodes. It's dying because it's evaporating. It's shedding mass so fast that it may lose a significant fraction of its total mass before the core collapse even happens. The ultimate fate depends on how much mass is left when the core finally gives out. That determines whether we get a neutron star or a black hole. And we can't predict that precisely because the mass loss rate fluctuates. The star is in a race between evaporation and collapse. Will the core run out of fuel first? Or will the star shed so much mass that the core collapse produces something different than it would have otherwise? This is dynamic equilibrium. The star exists in a constant state of falling apart. The core generates energy. That energy drives convection. Convection lifts material. Radiation pressure pushes dust. Dust drags gas. Gas escapes. The star gets lighter. Gravity weakens. Escape becomes easier. The cycle continues. There's no endpoint where the star settles down. No stable configuration. It's a temporary structure held together by forces that are actively working to tear it apart. The only reason it exists at all is that the core generates energy fast enough to replace what's lost, for now. Think about standing on the surface of Stephenson 2-18. Not that you could. There's no surface in the way we think of one. Just layers of gas getting progressively denser as you descend. But imagine you could stand there somehow. You'd watch streams of gas rising past you, dust grains forming out of the cooling atmosphere, flowing upward, accelerating. You'd be standing in a hurricane that never ends. A wind moving at tens of kilometers per second, carrying the star's own body into the void. And you'd know that the ground beneath you isn't solid. It's more wind, more convection. Everything is moving. Everything is temporary. The star weighs something like 16 times the sun's mass. Maybe more. Measurements are difficult, but let's say 16 solar masses. At the current mass loss rate, it loses one solar mass every 5 to 10,000 years. It's already lived a few million years since it became a red supergiant. Do the math. It's already lost a substantial amount of its original mass. The star we see today is lighter than the star that was here 10,000 years ago, and it will be lighter still 10,000 years from now, if it lasts that long. This is not a static object, not a thing you could point to and say, there, that's the star, unchanged. It's a process, a flow. Material moves through it. Energy radiates from it. Mass escapes from it. The star is more verb than noun. We give it a name and a catalogue number, and we talk about it like it's a fixed thing, but it isn't. It's a temporary configuration of matter and energy that happens to be occurring right now. In the grand scheme, it's barely been here at all, and it won't last. But before we can grasp the process, We need to understand the stage it's happening on, the sheer physical scale of this star. We've talked about what it is and how it behaves, what it's made of and how it's dying. None of that means anything if you can't picture the actual size of the thing. So let's try. Let's measure it the only way that makes sense, by crossing it. Light takes about 3 hours to cross the diameter of this star. 3 hours. That's the time it takes you to watch a movie, finish it, and watch it again. In that same span, light travels from one side of the star to the other. Light moves at 670 million miles per hour. It crosses the distance from Earth to the Moon in 1.5 seconds. It reaches the Sun in 8 minutes. And it takes 3 hours to cross this star. Think about that. Light doesn't wait. It doesn't slow down. It just goes. And even at that speed, crossing this star takes longer than your entire morning routine, longer than a flight across the country, longer than most people spend awake before lunch. Here's another way to see it. Light takes 43 minutes to travel from the Sun to Jupiter. That's the outer edge of the inner solar system, the boundary where the rocky planets end and the gas giants begin. Light crosses that entire distance, Sun to Jupiter, in 43 minutes. It crosses this star in 3 hours. The star's diameter is larger than the distance from the Sun to Jupiter. You could fit the entire inner solar system inside this star. Mercury, Venus, Earth, Mars, the asteroid belt, and Jupiter. All of it, with room to spare. The size isn't abstract. It's not some vague notion of bigness. It's measurably, demonstrably larger than the space we think of as the solar system, the space we imagine when we picture our cosmic neighborhood. This star is wider than that entire neighborhood. Let's slow down. Forget light for a moment. Let's use something more familiar, an airplane, a commercial jet traveling at 500 miles per hour, a speed you've probably experienced, a speed that feels fast when you're 30,000 feet up, watching the ground blur beneath you. At that speed, crossing this star would take 400,000 years. You'd board the plane before modern humans existed, before Homo sapiens left Africa, before we learned to speak or make art or bury our dead. You'd fly through the entire history of our species, every civilization, every war, every discovery, and you still wouldn't be halfway across. The plane would arrive 400,000 years from now, long after every language spoken today has vanished, long after every city has crumbled, long after the constellations have shifted into shapes we wouldn't recognize. Let's go faster. The fastest object humans have ever built is a spacecraft called New Horizons. It travels at 36,000 miles per hour. It flew past Pluto and kept going, out into the dark beyond the planets. At that speed, crossing this star would take 6,000 years. You'd launch the spacecraft at the dawn of agriculture, when humans first planted seeds and built permanent settlements, when we invented writing and the wheel and the concept of recorded history. The spacecraft would cross the star and arrive today, 6,000 years of human civilization compressed into a single crossing. That's not fast enough. Let's try something slower. Let's walk. If you could walk across this star at 3 miles per hour, which you can't, but hypothetically, it would take 450 million years. 450 million years. That's longer than complex life has existed on Earth. You'd start walking in the Cambrian period, before the first fish evolved, before anything crawled onto land, before there were trees or insects or dinosaurs or mammals. Yet you'd walk through the entire history of vertebrate life, through mass extinctions and ice ages, and the rise and fall of ecosystems we can barely reconstruct. And you'd finish walking today, every fossil you've ever seen in a museum, every ancient creature preserved in stone, every ancestor in the long chain that led to you. All of that history would unfold while you walked, one foot in front of the other. For 450 million years, the human brain isn't built for this. We evolved to understand distances we can see, distances we can walk in a day or a week. We can stretch that understanding a little. We can imagine the distance to the next city or across an ocean. We can almost grasp the distance to the moon if we think hard enough. But this breaks something fundamental. There's no intuition here. No gut feeling that helps. You can do the math. You can write down the numbers. But you can't really feel it. The star is so large that our usual tools for comprehension just stop working. Speed becomes meaningless. Duration becomes meaningless. You can say 3 hours or 400,000 years or 450 million years, and none of it connects to anything you've experienced. The numbers are accurate, the comparisons are real, but the understanding isn't there. It can't be. We exist at a particular scale, a human scale, where seconds are short and hours are long, and years are significant, where a mile is a meaningful distance and 1,000 miles is far. This star exists at a scale so far removed from ours that the two barely touch. We can measure it. We can describe it. We can calculate how long it would take to cross at any speed we choose. But we can't truly comprehend it. Not in the way we comprehend the size of a room, or a building, or even a mountain. The star is simply too large for us. Too large for the species that discovered it. We've found something that exceeds the limits of human-scale thinking, and all we can do is catalogue it, measure it, try to explain it in terms that might mean something, even though we know, on some level, that the terms will never be enough. And yet, we keep trying. We keep searching for the comparison that might work, the frame of reference that might make it click. Let's try counting. 1 sun-sized volume per second, just counting. 1, 2, 3. You could count all day, all week, all year. If you counted 1 sun-sized volume per second, it would take 317 years to count to 10 billion. Longer than the United States has existed. Longer than anyone has used electricity. You'd start counting before Mozart was born and finish sometime around now, just to count the volumes of our own sun that fit inside Stephenson 218. That's not a star. That's a warehouse of stars. The surface area is over 4 million times the sun's surface area. 4 million. Imagine wrapping the sun in paper. Now imagine you need 4 million sheets that size to wrap Stephenson 218. The amount of starlight radiating from that surface at any given moment is enough to make our sun look like a penlight in a stadium. The luminosity ranges from 440,000 to 630,000 times brighter than the sun. We're not exactly sure where in that range it sits. The measurements are difficult at this distance, this dust, this scale. But even at the low end, 440,000 times brighter means something almost incomprehensible. If you could capture all of Stephenson 218's light output for 1 second, just 1 second, and convert it to electricity, you could power every human city, village, and device for 10,000 years, the entire span from the first farms to the space age. Every light bulb, every computer, every car and plane and factory and phone. At 10,000 years of human energy consumption, paid for by 1 second of starlight. 1 second. The star is pumping that much energy into the void every moment of every day, and almost all of it goes nowhere, hits nothing, just radiates out into empty space forever. But some of it comes here, to us, to Earth, and that light has a story. The distance from Earth is 20,000 light years. 20,000 years of light travel. At 300,000 kilometers per second, light crosses that gap in 20,000 years. The light reaching your telescope tonight left Stephenson 218 20,000 years ago, during the last ice age, when mammoths walked the earth and humans were hunter-gatherers living in small bands, when agriculture didn't exist, when cities didn't exist, when writing didn't exist. Yet you're not seeing the star as it is. You're seeing its past. Every photon hitting your eye left that star before civilization began, before anyone built anything permanent, before anyone planted a crop or domesticated an animal or invented the wheel. The light has been traveling through empty space for the entire span of humanity's rise, from caves to cities, from stone tools to space telescopes. All of it happened while those photons crossed the void. What does that mean? Really mean? You're looking at a telescope image of Stephenson 218, and the light in that image is older than the pyramids, older than Stonehenge, older than the wheel. The star you're seeing doesn't exist anymore, not as it appears. It might be slightly different now. It might be gone. You're seeing a ghost transmitted across the void, from an age before history. We are not observing the star. We are observing a 20,000-year-old recording of the star. The star could have exploded into a supernova 10,000 years ago, a blast so bright it would briefly outshine the entire galaxy, and we wouldn't know yet. The light from that explosion is still on its way, still crossing the gap. It might arrive tomorrow. It might arrive in another 10,000 years. There's no way to know. The information travels at light speed. Nothing goes faster. We can't check. We can't call ahead. We just wait and watch the past. There's something profound about that. You have more ancestors going back 20,000 years than Stephenson 218 has sun volumes. Actually, wait, let me check that. No, I had it backwards. Stephenson 218 has 10 billion sun volumes. You have maybe 1 trillion ancestors going back 20,000 years. Okay, you win, but barely. The point is accumulation, time and accumulation. 20,000 years is enough time for an entire species to change, to go from scattered groups to a global civilization. Enough time for ice ages to come and go, for coastlines to shift, for forests to grow and die and grow again. And a photon doesn't care. It just travels, crosses the gap, arrives. You catch it in a telescope, point a sensor at the sky, collect a few thousand photons, process the data, make an image, and what you get is a snapshot of a star that might not exist anymore. A star so massive it might have already torn itself apart, blown its outer layers into space, collapsed into a black hole. Or it might still be there, burning, radiating, fusing elements deep in its core. You won't know until the light tells you, and the light is always 20,000 years behind. That's the weight of distance. Not just the space between us and the star, the time between us and the star, the gap in information. We're looking backward through time with every observation, every photograph, every measurement. The universe we see is not the universe that exists, it's the universe that existed, however long it took the light to reach us. For Stephenson 218, that lag is 20,000 years, 20 millennia of uncertainty. We see where it was, what it looked like, how bright it shone, but we don't see what it is. We can't. The information hasn't arrived yet, and it won't. Not in your lifetime, and not in anyone's lifetime for another 20,000 years. The star is effectively frozen in the past, a monument to an age when humans hadn't yet learned to write, when the concept of history didn't exist because there was no way to record it. That star has been shining all this time, through every empire, every war, every discovery, every invention, shining into the void. And we've only just now received the message. We've found one of the largest stars in the universe, and we're looking at it the way it was when we were hunter-gatherers. The universe is vast, but time makes it vaster. Inside Stephenson 218, there's a furnace, but not the kind you're imagining, not one chamber with one flame. This is a furnace with layers, concentric shells of burning elements stacked one inside the other, each layer producing ash that sinks down and becomes fuel for the next. It's structured like an onion, layers of burning elements, each shell producing the ash that fuels the next layer down. Hydrogen in the outer envelope, helium deeper in, carbon below that, then neon, then oxygen, then silicon, and at the very center, iron accumulates, growing, waiting. The hydrogen shell burns in the outer layers. It's fusing into helium, releasing energy, pushing outward against gravity. That helium sinks deeper into the star where temperatures and pressures are higher, hot enough for helium fusion. 3 helium nuclei combine to form carbon. The carbon sinks even deeper. The temperature rises. Carbon fuses into neon and oxygen. Those elements sink and fuse into heavier elements still. Silicon forms, then iron. Each stage happens in its own shell and its own layer of the onion. The star isn't burning uniformly, it's burning in zones, distinct regions where specific fusion reactions dominate. This structure exists because of temperature gradients. The center of the star is the hottest region, the only place hot enough for silicon fusion. Moving outward, each layer is slightly cooler, supporting only the fusion reactions that can occur at those temperatures. Hydrogen needs 10 million degrees, Helium needs 100 million. Carbon needs 600 million. Silicon needs 3 billion. The star sorts itself by temperature. The heaviest elements burn at the core. The lightest elements burn in the outer shells. It's a natural stratification. Physics organizing itself. Each fusion stage releases energy, but not the same amount. Hydrogen fusion is efficient. You get a lot of energy per reaction. Helium fusion is less efficient. Carbon fusion gives you even less. By the time you reach silicon fusion, you're getting diminishing returns. The star is working harder for less energy. It's burning through fuel faster just to maintain the same outward pressure. The pace accelerates. Hydrogen burns for 10 million years. Helium for 1 million years. Carbon for 1,000 years. Neon for a single year. Oxygen for months. Silicon for days. Each fusion stage lasts shorter than the last. It's accelerating toward death. Think about that progression. 10 million years of hydrogen. 1 million years of helium. 1,000 years of carbon. Then silicon burns for days. Not years, not months. Days. After millions of years of relatively stable burning, the star sprints toward its end in less than a week. As it's like a person aging normally for 80 years, then going from middle-aged to dead in the span of a single morning. The end comes suddenly, violently, without warning. The silicon burning phase is the final stage. Silicon nuclei fuse together, building heavier and heavier elements through a cascade of reactions. Sulfur, argon, calcium, titanium, chromium. The reactions move up the periodic table, one step at a time, until they reach iron. Iron is element 26, 26 protons in the nucleus. It sits at a very specific position on the curve of nuclear stability. It is the most stable nucleus in the universe, and that stability is a death sentence for the star. Iron is nuclear ash, the final waste product of stellar fusion, the point where you can't extract any more energy. Fusing elements lighter than iron releases energy. That's what powers stars. But fusing iron absorbs energy. It takes more energy to force two iron nuclei together than you get back from the reaction. Iron is a dead end. It's like a bank account that only accepts deposits, never pays interest. Once you have iron, fusion stops being profitable. The star can't use it as fuel. It just accumulates. Every second, the silicon-burning shell converts more silicon into iron. The iron core grows. 1 solar mass, 1.2 solar masses, 1.3 solar masses. The core is inert. It's not fusing. It's not producing energy. It's just sitting there, held up by electron degeneracy pressure, a quantum mechanical effect where electrons resist being squeezed into the same space. It's not thermal pressure. And the core isn't hot enough to fight gravity with heat. It's fighting gravity with quantum mechanics, with the fundamental principle that two electrons can't occupy the same quantum state. Electron degeneracy pressure is strong, but it's not unlimited. There's a threshold, a maximum mass that electron degeneracy pressure can support, 1.4 solar masses. That number is called the Chandrasekhar limit, named after the astrophysicist who calculated it. It's a hard boundary. Below 1.4 solar masses, electron degeneracy pressure holds. Above 1.4 solar masses, it fails. The electrons can't resist anymore, and when the pressure fails, there's nothing left to hold the core up. The iron core approaches that limit. 1.39 solar masses, 1.395, 1.399. Yet it's gaining mass from the silicon-burning shell above it. Thousands of tons per second converted from silicon to iron and added to the core. The star has no way to stop this process. It's committed. The core will reach 1.4 solar masses. It's only a question of when. The rest of the star doesn't know what's happening. The outer layers are still burning hydrogen, still fusing helium, still releasing energy and light into space. From the outside, Stephenson 218 looks stable, a massive red hypergiant, shining steadily into the void. But at the center, in a region smaller than Earth, an iron core is growing, approaching a threshold, preparing for collapse. The star is a bomb with a lit fuse, and the fuse is almost gone. Stephenson 218 is not alone. The universe has made other monsters, Other red supergiants, burning through their final years, swollen to sizes that challenge comprehension. And we've found them. Betelgeuse in Orion, V Canis Majoris in the southern sky, Ui Scuti in the constellation Scutum. Each one is enormous. Each one is dying. Each one is a laboratory for understanding how the most massive stars end their lives. But here's the thing, we don't actually know which one is the largest. The rankings change. The measurements shift. What held the record 5 years ago might be smaller than we thought. What looks smaller today might pulsate outward tomorrow and reclaim the crown. Red supergiant size rankings are like trying to rank clouds by size. They're constantly changing shape, pulsating, ejecting material, with no hard edges. Today's champion might be tomorrow's runner-up. The stars don't hold still long enough for us to be certain. Ui Scuti held the record before Stephenson 218. For years, it was the largest known star in the universe. Astronomers measured its radius at roughly 1,700,000,000 kilometers. That's about 1,200 times the radius of the Sun. If you placed it at the center of our solar system, its surface would extend past Jupiter's orbit. Jupiter itself would be inside the star, vaporized, gone. The entire inner solar system would fit inside Ui Scuti with room to spare. Then we got better data, better instruments, better methods for measuring stars hidden behind dust and distance. The numbers changed. The uncertainty bands widened. Ui Scuti might be smaller than we thought, or it might be larger. So the star pulsates over a period of months or years. Its size changes. We can only measure what we see at the moment we look. V Canis Majoris held the record before that. Discovered in the 1800s, studied for over 2 centuries, and for a long time, considered the largest star we'd ever found. Its radius was estimated at around 1,420,000,000 kilometers. That's roughly 1,000 times the Sun. But the measurements were uncertain. The star is surrounded by thick clouds of dust it ejected thousands of years ago. The dust scatters light, distorts measurements, makes it hard to tell where the star ends and the nebula begins. We were trying to measure a star through a fog of its own making. The problem is fundamental. Red supergiants don't have hard boundaries. Their outer atmospheres are so diffuse that density falls off gradually. There's no clear edge, no surface you could stand on, if you could somehow survive the heat and radiation. Just gas getting thinner and thinner until it blends into the interstellar medium. Defining the radius means choosing an arbitrary density threshold. Different thresholds give different sizes. Different methods give different results. The stars also pulsate. Their outer layers expand and contract over periods of months or years. A red supergiant might be 5% larger this year than last year, then 5% smaller the year after. The pulsations are driven by instabilities in the star's interior. Pressure waves ripple outward, causing the surface to rise and fall like the skin of a drum. The star breathes. It swells and shrinks. Any measurement we take is just a snapshot of a moment in that cycle, and they're ejecting material. Stellar winds carry mass away from the surface at rates of 10 to the -4 solar masses per year. That's about 1 Earth mass every 3,000 years. It doesn't sound like much, but over millennia, it adds up. The material forms shells and clouds around the star, further complicating observations. We're trying to measure a moving target that's hiding behind its own exhaust. Betelgeuse is the most famous of the red supergiants. It's the bright red star in Orion's shoulder, visible to anyone who looks up on a winter night. It's close, only about 550 light-years away. That's practically next door in cosmic terms. Close enough that we can study it in detail. Close enough that we've measured its surface with interferometry. Close enough that when something happens, we notice. And in late 2019, something happened. Betelgeuse started dimming, rapidly. By January 2020, it had lost more than half its brightness. For a star that's normally one of the 10 brightest in the night sky, that's dramatic, visible. People noticed, astronomers noticed, and the internet lost its mind. When Betelgeuse dimmed in 2019, the internet lost its mind. It's going to explode. We'll see a supernova in our lifetime. And astronomers were like, probably not. It's probably just dust. And it was just dust. Betelgeuse was not dying, merely sneezing. The star is fine. Well, not fine. It's a red supergiant, so it's definitely dying. But not imminently, probably. But we think. The dimming event turned out to be caused by two factors. First, a large convective cell on the star's surface cooled, reducing its luminosity. Imagine a dark spot, like a sunspot, but covering a significant fraction of the star's visible hemisphere. Second, the star ejected a cloud of dust. The material condensed as it cooled, forming particles that blocked light from reaching Earth. It was like the star coughed up a smoke cloud that drifted between us and it. The dust eventually dispersed. The convective cell warmed back up. Betelgeuse brightened. By mid-2020, it was back to normal. It's like a person sneezing and everyone thinking they're dying. It was dramatic, visible, but not fatal. The star wasn't collapsing. Its core wasn't imploding. It was just doing what red supergiants do, pulsating, ejecting material, being unstable. This is normal behavior for a star in this phase of life. Uncomfortable to watch, perhaps, but normal. The event taught us something. It showed that red supergiants can undergo rapid, dramatic changes that have nothing to do with core collapse. The dimming looked alarming from Earth, but it was surface-level activity. Literally, the core was fine, the fusion shells were fine, the star was still fusing elements, still producing energy, still holding itself up against gravity. The drama was all in the outer layers. It also reminded us how much we still don't understand. We didn't predict the dimming. We couldn't have predicted it. We don't have models good enough to forecast convective cell behavior or dust ejection events in red supergiants. We're still learning, still watching, is still trying to understand what these stars do in their final years. All these stars are in the same boat. Huge, cool, unstable, dying. It's like a hospice ward for the galaxy's most massive stars. They're all in the red supergiant phase, burning helium in their cores or beyond. They're all enriching the galaxy with heavy elements through their stellar winds. They're all headed for the same fate. Core collapse, supernova, either a neutron star or a black hole left behind. The details might differ, but the endpoint is the same. Betelgeuse will explode, VY Canis, Majoris will explode, UY Scuti will explode, Stephenson 218 will explode. The only question is when. For Betelgeuse, it might be tomorrow, or it might be 100,000 years from now. For the others, even farther away and harder to study, the timeline is even less certain. We can't predict supernova timing with any precision. We can only say that it will happen, eventually, on cosmological timescales that are fast, but still beyond human lifespans. What we learn from studying these stars collectively is more valuable than what we learn from any single example. Each red supergiant gives us a different view of the same evolutionary phase. Betelgeuse is close, so we see fine details. VY Canis Majoris has an extensive nebula, showing us how mass loss shapes the environment. A UI Scuti and Stephenson 218 push the upper limits of size, testing our models of stellar structure. Together, they paint a picture of what happens when stars 20 or 30 or 40 times the sun's mass reach the end of fusion. And there might be more, larger stars we haven't found yet. The galaxy is big, dust is everywhere. Infrared surveys are still incomplete. There could be a red supergiant out there, hidden behind a particularly thick dust cloud, larger than Stephenson 218, larger than anything we've measured. We wouldn't know. We can only catalogue what we can see. The title, Largest Star Ever Discovered, is really the largest star we've measured so far with our current instruments and methods. It's provisional, pending better data, pending better telescopes, pending a more complete survey of the galaxy's most obscured regions. The record might change again. It probably will. That's how science works. We measure what we can, with the tools we have, and we accept that the answers might shift when the tools improve. The rankings don't really matter. Whether Stephenson 218 is the largest or UY Scuti or some star we haven't found yet, the scale is incomprehensible either way. They're all enormous. They're all dying. They're all teaching us about the limits of stellar evolution. The question isn't which one wins. The question is what they tell us about how the universe makes and destroys its most massive objects. And what they tell us is this: stars this large are rare, unstable, short-lived, they burn fast, live briefly, and die violently. You see, they represent an extreme edge case of physics, where gravity and pressure and fusion push matter to configurations that can barely hold together. They exist in a state of constant crisis, held up only by the furious energy production in their cores. When that energy stops, there's nothing left to save them. Stephenson 218 is part of a family of giants, but it's also alone, in a sense. Each of these stars is an individual, with its own history, its own structure, its own timeline toward collapse. We study them together to understand the pattern, but when one explodes, it will do so on its own terms, in its own time, becoming something new. When a hypergiant's iron core exceeds 1.4 solar masses, something fundamental breaks. Electron degeneracy pressure, the force that held the core together, as simply stops working. The core has no support left. Gravity wins. The collapse begins. This isn't a slow fall. The core implodes at approximately 0.25 the speed of light, 1/4 light speed. That's 75,000 kilometers per second. The entire iron core, about the size of Earth, collapses inward faster than anything you'll ever witness in nature outside a black hole. In less than 1 second, the core is squeezed from Earth-sized to city-sized. Picture crushing the entire planet down to the size of Manhattan in 1 second. That's the violence we're talking about. Every atom, every particle, compressed beyond recognition. The core keeps falling. Electrons are forced into protons. They merge, forming neutrons. The core becomes a ball of pure neutron matter, reaching nuclear density. And this is matter so dense that a teaspoon would weigh as much as a mountain. Neutrons themselves have a limit. They can't be compressed further. The core hits that limit. Then it bounces. Think of dropping a rubber ball onto concrete. The ball compresses when it hits, then springs back, sending a shockwave through itself. The core does the same thing. It compresses to nuclear density, can't go further, and rebounds. That rebound sends a shockwave racing outward through the collapsing star. This shockwave should blow the star apart. It should create the supernova. That's how the textbooks describe it. The shockwave stalls. It happens about 100 kilometers out from the core. The shockwave hits the outer layers of the star, still falling inward at tremendous speed. It's like a car hitting a wall of mud. The initial impact isn't enough to break through. It needs extra energy to push through. The shockwave loses momentum. It stops. For a brief moment, measured in milliseconds, the supernova fails. The explosion that should happen doesn't. The star should just collapse into itself, becoming a black hole without fanfare, without light. This is where something strange saves it. Something you wouldn't expect. Neutrinos. When the core collapses, it releases 99% of its energy as neutrinos. Not light, not heat. Neutrinos. These are particles famous for not interacting with anything. They pass through entire planets without touching a single atom. Trillions of them pass through your body every second from the sun, and you never feel it. They're ghosts. But during core collapse, the numbers become absurd. At 10 to the 58th power, neutrinos are released in about 10 seconds. That's more particles than all the atoms in every human who ever lived, more than every grain of sand on Earth, more than every star you can see with your naked eye, all released in less time than it takes to read this sentence. The shockwave sits there, stalled, dying, but it's sitting in a hurricane of neutrinos. Even though neutrinos barely interact with matter, when you have 10 to the 58th of them passing through a relatively small region, some of them interact, a tiny fraction. But that tiny fraction, multiplied by such enormous numbers, deposits enormous energy. The neutrinos heat the stalled shockwave. They dump energy into it. Slowly, over the course of a few hundred milliseconds, the shockwave revives. It gains strength. It starts moving again. And the supernova succeeds because of particles that are famous for not interacting with anything. That's the irony. The collapse is so violent, so energetic that the mechanical bounce isn't enough. It's the ghost particles, the ones that slip through everything, that actually drive the explosion. Without neutrinos, most supernovae would fail. The stars would collapse silently into black holes. We wouldn't see the fireworks. We wouldn't get the elements scattered into space. The universe would be a darker, quieter place. The revived shockwave pushes outward. It fights through the infalling outer layers. It takes time, measured in hours, for the shockwave to reach the surface of the star, but it's moving now. It has the energy it needs. The outer layers of the hypergiant, all those shells of oxygen and carbon and helium and hydrogen, are about to be blown into space at thousands of kilometers per second. The core, compressed to a ball of neutrons or collapsed entirely into a black hole, is left behind. The supernova is about to become visible. The shockwave is approaching the surface. When it breaks through, the star will brighten, not gradually, suddenly. From Earth, if anyone happens to be watching, they'll see a new point of light appear in the sky where nothing was before. But that's not happening yet. Right now, deep inside the star, the shockwave is still climbing, still fighting, still carrying the energy of a core that collapsed at a quarter the speed of light, revived by ghost particles that barely touch anything. The mechanics are complete. The collapse has finished. The bounce has happened. The neutrinos have done their work. But what happens when the shockwave breaks through? When the star finally shows the universe what it's been hiding inside? That's coming. But for this moment, the explosion is still eternal, still climbing, still gathering strength for what comes next. The shockwave breaks through. The surface of the hypergiant erupts all at once. The star that was 1,500 times wider than the Sun suddenly becomes a bomb visible across the galaxy. This is the supernova, the explosion we've been building toward, and it releases energy that most people can't comprehend, even when you write it down. 1 pho. That's the unit astronomers use, short for 10 to the 51 ergs, which doesn't help anyone, so they gave it a nickname, 1 Beth, after the physicist Hans Bethe, who figured out how stars burn. A 1 Beth equals 10 to the 44 joules, a 1 followed by 44 zeros. That's how much energy this explosion releases, not over years, over seconds. Let's ground that number. The entire Sun, burning for its whole 10 billion year lifetime, will release about 1 Beth of energy total. This supernova releases that much in the time it takes you to blink. Every nuclear weapon ever detonated on Earth, combined, releases about 10 to the 17 joules. This explosion is 10 billion trillion times more powerful than every bomb humans have ever built, detonated simultaneously. The star is converting the gravitational collapse of its core into light and motion. It's turning mass into energy at a scale that makes our most violent technologies look like candles. And it shows. From Earth, if we happened to be watching, we'd see a new star appear, not gradually brightening over weeks, just suddenly there. One moment, nothing. The next, a point of light where empty space used to be. For a few weeks, maybe months, that single dying star would outshine its entire host galaxy. 400 billion stars, all burning steadily, and one supernova drowns them all out. Picture this, 400 billion stars combined, every pinpoint of light in the Milky Way, gathered together. Now imagine one candle suddenly becoming brighter than every city on Earth simultaneously. Every streetlight, every car headlight, every screen, every building, all of it lit up at once, and one candle outshines the whole thing. That's the scale we're talking about. One star briefly becomes brighter than an entire galaxy of stars. The light is just the signal, and the real transformation is in what the explosion does to the star itself. The outer layers, all those shells of oxygen and carbon and silicon and iron, are ejected into space, not drifting, blasted, at approximately 10% the speed of light. That's 30,000 kilometers per second. In 1 second, the star's outer atmosphere travels a distance equal to 3/4 of the way around Earth. It's moving so fast that if you could somehow stand in its path, you wouldn't see it coming. It would hit you at the same instant the light from it reached your eyes. These layers contain everything the star built over millions of years: oxygen forged in the helium shell, carbon from earlier burning phases, silicon and sulfur from the final weeks, iron from the core, blown outward by the shockwave, heavier elements, gold and uranium and platinum, created in the explosion itself when neutrons slammed into lighter atoms faster than they could decay. All of it, every element heavier than helium, ejected into the surrounding galaxy at thousands of kilometers per second. This is how galaxies grow richer. This is how the universe becomes chemically complex. Stars like Stephenson 218 are seed bombs. They forge heavy elements in their cores over millions of years, then scatter them into space in seconds. Those elements drift through the galaxy. They mix with clouds of hydrogen gas. Eventually, they collapse into new stars, and some of those stars have planets, and some of those planets have the right mixture of elements to support something we call life. The oxygen in your lungs right now was forged inside a star like this, and the carbon in your DNA, the iron in your blood, the calcium in your bones, the gold in jewelry, the uranium in reactor cores, the silicon in computer chips. All of it came from stellar cores or supernova explosions. Every atom in your body except hydrogen and helium was created inside a massive star or during its violent death. You are made of stellar debris. Stephenson 218 isn't just a distant object we're observing. It's a preview of the process that made you possible billions of years ago, when other hypergiants died and seeded the galaxy with the elements that would eventually become Earth and you. But what's left behind? After the outer layers are gone, after the explosion fades, what remains at the center? We don't really know. That's the honest answer. And it depends on how much mass is left in the core after the explosion. If the remaining core is less than about 2 to 3 times the mass of the Sun, it becomes a neutron star. A ball of neutrons 20 kilometers across, spinning hundreds of times per second, with a magnetic field trillions of times stronger than Earth's. If the core is heavier than that limit, no force in the universe can stop it from collapsing further. It becomes a black hole, an object so dense that space itself warps around it, where nothing, not even light, can escape once it crosses the boundary. For Stephenson 218, we can't predict which one it'll be, because we don't know exactly how much mass the star has lost over its lifetime. Hypergiants shed mass through stellar winds. They blow off their outer layers constantly for millions of years. How much mass remains when the core collapses determines what kind of remnant forms, and we can't measure the mass loss rate precisely enough to know. It's like watching a car crash in slow motion and trying to predict whether the engine will survive or be completely destroyed. You know the collision is happening. You can see the forces involved, but the outcome depends on details you can't measure yet. How fast it was going at the exact moment of impact, how the frame crumpled, where the stress concentrated. Stephenson 218 is the same. We know it will collapse. We know it will explode. But whether it leaves behind a neutron star or a black hole depends on variables we can't pin down from 20,000 light years away. What we do know is that something will remain, some dense object, impossibly small compared to the original star, sitting at the center of an expanding cloud of debris, a remnant, a fossil, a marker of where a hypergiant once lived and died. The explosion will fade over months. The ejected shells will keep expanding for thousands of years, glowing as they slam into surrounding gas. Eventually, they'll disperse entirely, mixing with the interstellar medium. The heavy elements will drift. Some will be incorporated into new stars, some into planets, some, billions of years from now, into living things that look up at the sky and wonder where they came from. That's the aftermath. Energy, light, motion, enrichment, and uncertainty about what's left behind. The star doesn't end cleanly. It transforms into light that travels forever, into elements that build new worlds, into a remnant whose nature we can only guess at. The hypergiant dies, but its influence doesn't. It spreads outward, seeding the galaxy, changing everything it touches. One star becomes a billion futures. We've talked about how Stephenson 218 will die, but first, Let's talk about why it can't be any bigger, why the universe has limits for stars, and what those limits tell us about physics itself. There's a theoretical cap on how massive a star can be when it's born, somewhere between 150 and 300 times the mass of the Sun. We call this the Eddington limit region. It's not a hard wall, more like a zone of instability. Stars above this mass don't settle into stable fusion. The radiation pressure from their cores is so intense that it blows the star apart before it can even finish forming. And it's like trying to build a house out of feathers held together by gravity. The wind from your own breath, the radiation pressure, blows it apart before you finish building. The star can't win against its own light. Think about that. A star can generate so much energy that it destroys itself just by shining. Not over billions of years. Right away, from birth, we've never observed a star being born with more than about 300 solar masses. Not once, despite searching, despite no obvious theoretical reason why more massive stars couldn't form from the right kind of gas cloud. It's possible that stars above a certain mass threshold simply can't exist. They'd be unstable from birth, blowing themselves apart before igniting fusion. The limits we observe might be fundamental, written into the physics of matter and gravity. Now here's where it gets interesting. Stephenson 218 started with only 25 to 40 solar masses. That's huge by most standards, massive enough to burn hot and die young. But it's not anywhere near the theoretical limit. It's not even close to the most massive stars we know about. So how did it become the largest star we've ever found? Evolution, time, expansion during the red supergiant phase. The largest stars are not the most massive, they're the most evolved. Size and mass are different things, controlled by different physics. A giant balloon versus a small dense ball of lead. One takes up enormous space, but weighs almost nothing. The other fits in your hand, but you can't lift it. Stephenson 218 is the balloon, bloated, diffuse. Its mass spread across a volume so large it defies comprehension. But evolution has limits too. As a red supergiant expands, its surface gravity gets weaker. Way out at the photosphere, 20,000 times farther from the core than Earth is from the Sun. Gravity is barely holding on. The star's own radiation pushes material away. Stellar wind, mass loss. Stephenson 218 is evaporating, constantly, losing material into space at a rate we can barely measure. This sets another limit. It's like trying to inflate a balloon with holes in it. At some point, the air leaks out faster than you can blow it in. A star can only get so large before the surface gravity is so weak that the star evaporates faster than it can evolve. The outer layers just drift away. The star can't maintain its structure. It collapses inward, or blows itself apart, or some combination of both. Stephenson 218 may be close to that practical upper limit, not the limit of mass, the limit of size. We don't know exactly where that limit is. The physics at these extremes gets messy. Radiation pressure, gravity, mass loss, magnetic fields, rotation, all competing, all trying to tear the star in different directions. The math breaks down. Models diverge. We're left with observations and guesses. The extremity of Stephenson 218 didn't come from its birth. It came from its life, from millions of years of fusion, expansion, and mass loss, from the specific conditions that allowed it to swell without tearing itself apart. The star is an accident of timing, born massive enough to evolve quickly, not so massive that it exploded early, caught in the red supergiant phase at just the right moment for us to see it. Yet we built telescopes to see farther, and what did we find? That we'd been missing most of the universe. We built better telescopes to see through dust and found stars larger than we thought possible. Every time we look closer, the universe gets weirder, which makes me wonder, what are we still missing? What's hiding in the next wavelength, the next generation of instruments, waiting to violate our intuition all over again? The limits we've found might not be the real limits. They might just be the limits of our current understanding. There could be stars out there, hidden in dust clouds or distant galaxies, that break every rule we think we know. Larger than Stephenson 218, more massive than 300 suns, doing things we haven't imagined yet. Or maybe we've found the actual limits. Maybe the universe really does have boundaries written into the fabric of physics. Maximum mass, maximum size. Lines that cannot be crossed, no matter how much gas collapses or how long a star evolves. The universe saying, this far, no farther. We don't really know. That's the honest answer. Stephenson 218 sits at the edge of what's possible. A star so large it might be testing the limits of stellar physics itself. It tells us that size and mass are separate, that evolution matters more than birth, that the biggest things aren't always the heaviest, and it tells us that even at the extremes, the universe follows rules: gravity, radiation, pressure, mass loss. The same physics that governs the sun also governs hypergiants. The scale changes, the numbers become absurd, but the rules stay the same. That's the lesson. Not that Stephenson 218 is impossible, that it's barely possible. Perched on the edge of existence, one variable different, and it wouldn't be there at all. Stephenson 218's red supergiant phase lasts roughly 100,000 years. That's how long it spends in this bloated, dying state. 100,000 years out of a 20 million year lifespan, 0.5%, at the last half of 1% of its existence. We're watching the final act, the curtain call, the moment before the star stops being a star and becomes something else entirely. Watching Stephenson 218 is like catching a single snowflake in a blizzard. This exact moment, this exact configuration will never happen again. The star is changing, dying, vanishing while we watch. Every second, it loses mass. Every year, it evolves. The thing we're observing right now is already different than it was when we first measured it. And by the time anyone reads this script, it will have changed again. The light we see left the star 20,000 years ago, during the last ice age, when humans were painting caves and hunting mammoths, when glaciers covered half of North America. So the photons that hit our telescopes today started their journey before civilization existed, before agriculture, before we had words for things like stars or distance or light. They traveled through the darkness for 20 millennia, and they arrived just in time for us to build machines capable of understanding what they mean. The star may already be dead. We won't know for thousands of years. If Stephenson 218 exploded tomorrow in its reference frame, the light wouldn't reach us until the year 22,000. Our great-great-great-grandchildren, hundreds of generations removed, would be the first to see the flash. Right now, at this exact moment, the star could be gone. A supernova, a neutron star, a black hole, and we'd still see it shining, because the light telling us about its death is still on the way. Of future observers, 100,000 years from now will point their telescopes at Scutum and see a rapidly expanding cloud of gas, glowing with the heat of a recent explosion, and in the center, a neutron star or black hole, the crushed remains of something that was once unimaginably vast. They will see the after, we see the before. The moment between is ours. The privilege of witnessing this star in its final days belongs to this era. This slice of cosmic time, this brief window when humanity exists and Stephenson 218 is still a star. Think about what that means. We are insignificant, one species on one planet, orbiting one star in a galaxy of 400 billion stars. And yet, we built machines to measure a star 20,000 light-years away, calculated its size to within a few percent. They predicted its death down to the mechanism. Insignificant, but not powerless. Small, but not blind. We figured out how to see through walls of dust, how to measure things we can never touch, how to understand a dying star from across the galaxy using nothing but the faint whisper of its light. This is the part that gets me. We are made of the same material as Stephenson 218. The carbon in our cells, the oxygen we breathe, the calcium in our bones, all of it was forged inside stars like this one. Stars that lived and died before our sun was born. We are not separate from this story. We are part of it. The star is us. We are the star, scattered and reassembled into forms that can think and wonder and measure. The universe made us from the ashes of dead stars, and we turned around and figured out where we came from. The search continues. Astronomers are still looking for larger stars, more extreme objects hidden in the galaxy. Maybe there's something bigger than Stephenson 218 waiting to be found. Maybe there isn't. Either answer tells us something about the universe, about the limits of what's possible, about the rules written into physics itself, and either way, we'll keep looking, because that's what we do. We point our instruments at the sky and we ask questions. How big? How far? How long? Why? Remember those photons that left during the last ice age that never made it through the dust? The ones that died in the dark? We found them anyway, not by waiting for them to arrive, but by looking in a different wavelength, by building new eyes to see what was hidden. The star tried to hide. We found it anyway, and now we know. Somewhere in the constellation, Scutum, hidden behind a wall of dust, the largest known star in the universe is dying, and we're watching. We've been watching for 20,000 years. We just didn't know it until now. If you enjoyed this, consider subscribing for more explorations like this one. There are more hidden wonders waiting, more questions to ask, more light traveling through the dark, carrying stories we haven't heard yet. The universe is vast, but we are looking.